Assalamualaikum warahmatullahi wabarakatuh and good evening. We are from group 6. We'll explain about the co-current example from the textbook. Next slide. Okay, the example is for the butane isomerization. When plant engineer Maxwell Anthony look up the vapor pressure at the exit to the adiabatic reactor in example 11.3, where the temperature is 360 Kelvin, he learned the vapor pressure was about 1.5 megapascal for isobutane, which is greater than the rupture pressure of the glass vessel the company had hoped to use. Fortunately, when Max looked in the storage shed, he found there was a bank of 10 tubular reactors, each of which was 5 meter cube. The bank reactors were double pipe heat exchanger with the reactants flowing in the inner pipe with UA equal to 5,000 kilojoule per meter cube per hour per Kelvin. Max also bought some thermodynamic data from one of the companies he found on the internet that did calorimeter experiments to find delta H reaction for various reactions. One of the companies had the value of delta H reaction for his reaction on sale this week for the low price of $25,000. For this value of delta H reaction, the company said it is best to use an initial concentration of A of 1.86 mol per dm cube. The entering temperature of the reactants is 305 Kelvin and the entering coolant temperature is 315 Kelvin. The mass flow rate of the coolant is 500 kilogram per hour and the heat capacity of the coolant is 28 kilojoule per kilogram per Kelvin. The temperature in any one of the reactors cannot rise above 325 Kelvin. Carry out the following analysis with the newly purchased values from the internet. The concurrent, the question asks to plot the X, XE, T, TA and negative RA down the length of the reactor. Next. From the example, the additional information that we get is from example 11.3 that CPA is equal to 141 kilojoule per kilomole per Kelvin and CPO is equal to 159 kilojoule per kilomole per Kelvin, and the data from the company Maxwell got off the internet or delta H reaction is equal to negative 34,500 kilojoule per kilomole with delta CPA equal to 0 and the CA naught equal to 1.86 kilomole per meter cube.
Okay, next I will explain the solution for this example. Firstly, we have to find the total flow rate, which is 0.9 is 90% of the component and 163 is the flow rate inlet. We divide by 10 because we have 10 reactors in parallel. So we get 14.7 kilomole per hour for this substance. Next, we will continue to find mole balance, rate law, and stoichiometry. And we just use this formula, just same as the example 11.3. And lastly, we will find the energy balance to get this value.
Okay, now we are going to solve the coupled ordinary differential and explicit equation 11.3.1, 11.3.7, 11.3.10, 11.3.11 and 11.3.12 and 11.12.1 and the appropriate heat exchange balance using polymer. After entering this equation, we will enter the parameter values. By using co-current heat exchange as our polymer base case, we only need to change one line in the program for each of the other three cases and solve for the profiles of X, XE, the conversion, T, TA, the temperature ambient, and rate of reaction, negative RA, and not have to re-enter the program. So for co-current flow, the balance on the heat transfer fluid is contribute in this equation with TA is 310 Kelvin and V equals to 0. The polymer program and solution are shown in the table E12.1.1. Next. So this is the results we are getting from the polymer. So first, we are setting the polymer into differential equation. So we put all the differential equation that we have calculated before. So first, we have the differential equation for TA, second for the conversion X, and third for the temperature. So don't forget to include the parameters given in the equation. So we have around 12 parameters that we need to put in the calculation. So before we run the program, we need to tick the table and graph columns. So as we want the results to be come up with the graph and the table. So this is the result. So the table calculated values for DEQ variables, and we see that from the graph A, graph of the profile down the reactor for concurrent heat exchange by versus the temperature. So at some point the TA is greater than TA, but in the final point, the both of them will go into the same value. So B is the conversion. XE will go further away from the X because X, the conversion, the real conversion is moving from the zero value into same value as XE at some point. So for the reaction rate, at some point it will be maximum around 0.5 to 1.0. Assume it is 0.7, but after that they will consume down into the last reaction. So next. So this is the analysis for what I have for what we discussed before. So we know that the reactor temperature goes through a maximum. Near the reactor entrance, the reactor concentration are high, and therefore the reaction rate is high. And QG is greater than QR. So consequently, the temperature and conversion increase with increasing reactor volume, while the XE decreases because of the increase in temperature. Eventually, X and XE come close together, which is V equals to 0.95 meter cube, and the rate becomes very small as the reaction approach equilibrium. So at this point, the reactant conversion X cannot increase unless XE increase. I repeat, at this point, the reactant conversion X cannot increase unless XE increase. So we also note that when the ambient heat exchanger temperature, the TA, and the reactor temperature T are essentially equal. Like I said before, it will comes equal at the some point after the reaction. There is no longer a temperature driving force to cool the reactor. So consequently, the temperature does not change further down the reactor, nor does the equilibrium conversion, which is only a function of temperature.
Okay, I think that's all from us. Hopefully you guys can understand what we are explaining for this question. That's all from us. Thank you.
Thank you, everyone.